So to conclude a little bit, our planner, in the limit, it returns a plan or an infeasibility proof. This is different from probabilistic completeness because it returns this infeasibility proof. But it's also different from the original definition of completeness because it does not guarantee return in finite time since it's using sampling. So here we define this term asymptotic completeness. So a planner is asymptotically complete if it returns a plan or an infeasibility proof in the limit. And so here, let's look at some experiments. So we did 2D and 4D CN experiments to show convergence. And in the 2D scenes, we also compared uniform sampling with Gaussian sampling. Even though all the analysis is based on uniform sampling from the analysis, we can see that the important samples are around the obstacle region boundaries. And then Gaussian sampling produces samples near obstacle regions. Gaussian sampling should help the manifold converge faster, which is what we see in experiments. In both scenes is the start scene and the mate scene. The blue line is the Gaussian line, red dashed line is the uniform line. We can see that the Gaussian converges faster than uniform. We also apply this on this 4DOF squirrel arm scene. This, as you can see, with more points sampled, it converges, success rates converges to 1. And the dashed line is a fitted exponential curve. So some dirty laundry. First is analysis of the validation step. Remember that we have 2 steps with learning step and validation. The validation step analysis is mentioned in the paper, but it's not rigorously proved. So this is partly because we still want to improve this validation step. Important part of future work is extending to higher dimension, where a large roadblock is this validation step. So validation step takes a large majority of runtime in up to 4DOF manipulators. And then along the years, we have went from 3DOF to 4DOF and now partially to 5DOF. And we think this framework could work for higher DOF manipulators, but it requires more engineering and algorithmic effort. And here is a summary of our contribution. We have shown convergence and exponential convergence for learn manifold being an infeasibility proof. And we have defined this new type of completeness, asymptotic completeness. Right. And thanks, that's the end of it.
Next speaker is Niels Wilde, postdoc at TU Delft, working with Javier Alonso Mora, and he was earlier both a postdoc and a PhD student at the University of Waterloo, where he worked with Dana Coolidge and
Yeah, hello everyone. My name is Niels Wilde, and I'm happy to present our paper, Error-Bound Approximation of Pareto Fronts in Robot Planning Problems today. The paper was written together by Alex Botras, Armin Sadeki, and Stephen Smith from the University of Waterloo, and Javier Alonso Mora and myself from TU Delft. So let's jump into it. In many robotics problems, we face the challenge that we want to simultaneously optimize multiple objectives or features. So we want to find a solution that minimizes a set of different objective functions. And one of the most common approaches to these types of problems is that we use a linear scalarization, where we put weights on these features, and we then solve a single objective optimization problem that minimizes this weighted sum. An important question remains, how can we find good weights for the scalarization such that we recover the a set of Pareto optimal solutions. That is the set of solutions where we can't improve any of the objectives without worsening at least one of the other objectives. And here in the figure on the right, we have an illustration when we use uniformly placed samples for scalarization. So here we have a motion planning problem with a Dubin's vehicle, and we want to minimize trajectory length and jerk. And we then just put down weights like in uniform increments and compute the corresponding trajectories. And as we can see, a lot of these trajectories look very similar to each other. And if we look at the Pareto front, our sampled Pareto front points in blue are all in one area. So that's not a very good representation. It would be much nicer if it looked like this. And today I'm going to show you an algorithm that can compute samples for scalarized optimization that look like this. So why do we care about this? Why do we need good scalarization weights? The simple reason is that we can't compute all possible trade-offs in multi-objective optimization, especially not when doing this online. So what we often do is that we pre-compute a set of solutions, and this set should be as diverse as possible so that we can explore different options. And this has many applications. I just want to highlight two of them. One is reward learning, where we want to learn a reward function that represents a user's preference for how a robot should behave. However, most of the algorithms in reward learning require pre-computed trajectories, and having good trajectories at hand can help these algorithms. Another application is computing presets for robot behavior, for instance, driving styles for an autonomous car. Or if you have a multi-robot pickup and delivery problem, you want to explore the trade-offs between minimizing operation cost and maximizing quality of service. And since this problem is very cumbersome to solve, it's crucial that you spend your pre-computed computation time wisely. So let's define this problem. We begin with two simple definitions. The first is the weight set. So the weights in our scalarization shall be positive vectors where the elements sum to 1. And second, we need some error function to describe how well we represent weights that we didn't sample. For this, we use the notion of regret. And in short, the regret of a weight WA under weights B expresses how good the optimal solution for weights A approximate the optimal solution for weights B. With this, we can now state our main problem. So given a linearly scalarized multi-objective planning problem and some budget K, we want to solve this nested optimization problem. So let's break it down. We start in the innermost optimization where we are given a set of pre-computed set of samples and the corresponding pre-computed trajectories or solutions that's shown in blue. And we're given some other weight where we want to approximate the corresponding optimal solution. That's the one in orange. So we then pick the one from our pre-computed set that does the best job at approximating. The maximization tells us that this orange solution that we want to approximate is chosen in a worst case manner. And now our job is to solve the outer approximation to pick a good set of pre-computed solutions. And all of this is subject to the constraints that we can't do more than K pre-computations. Okay, to solve the problem, we analyze the components of it. And first we take a look at this optimal cost. That is the objective value of our scalarized optimization problem as a function of the scalarization weights. And for any multi-objective optimization problem, this optimal cost is continuous and it's concave, with the only assumption being that these objective functions are bounded, so there's no infinities anywhere. Furthermore, we can compute the subgradient of that function by simply looking at the values of our features or our objective functions. So what does this tell us? Let's say we pick some weight W prime. Given that we have an exact solver for the scalarized version of the optimization problem, we will find the function value of this optimal cost function, and we get the tangent plane. And this now allows for a very powerful observation. If we want to approximate another weight, W star over here, using our pre-computed solution W prime, our regret is simply the difference between the tangent plane and that concave optimal cost function. So this gives us an idea on how we can use multiple samples to then approximate any other weight or the solution that is optimal for any other weight. So let's say we have n samples, where n is the number of objectives that we have in our problem. We can now bound this optimal cost function between the samples, and we can do that in two ways. We can do a linear interpolation of the objective values the function values, which will give us a lower bound that holds because the function is concave. And we can take the tangents from both of these samples, which then builds a nice roof over the function. And the lowest of these tangents will give us a tight upper bound at any point. And so now by bounding this optimal cost function, we are able to bound the regret that our samples will have with respect to any weight that we didn't sample. Okay, so here's how that works. We now want to bound the regret in a neighborhood. We use the word neighborhood here somewhat loosely. A neighborhood is just a collection of n linearly independent samples. That's what's shown at the bottom of the figure on the right. We have 3 samples that we picked, W1, 2, and 3. And they now span a subspace, which is, they span a convex hull. And now we want to bound the regret of any weight that lies inside that convex hull. And we begin by just defining our interpolation plane. That's the red plane at the top. So just the interpolation of the 3 function values that we computed. And to then get an upper bound of regret, we take the difference between the lowest tangent plane and the interpolation plane, which will always be an upper bound for the difference between the tangent plane and the actual function curve. So at each point, for each neighborhood, we can bound the regret. And since this only requires like a linear function for the tangents and a linear functions for the interpolation, we can find the weight inside the neighborhood where the regret bound is the largest using a linear program. So this now leads to our algorithm. What we do in the end is a greedy minimization of this regret bound, of this upper bound on the regret in neighborhoods. And we begin by one initial neighborhood that's constituted by the canonical basis of weights. We then find the weight W prime with maximum regret bound inside the neighborhood and just add that to our set of samples. So we just pick the one that's now represented worst and add it to our samples. And then we divide the neighborhood in n smaller neighborhoods by just swapping in W prime for any of the weights that constituted that neighborhood. We then repeat that algorithm, but now over a set of neighborhoods. So we search over them, compute this regret bound, always just using a linear program, and then pick the one where the regret bound is largest, add that sample, and divide that one neighborhood further. So here's an illustration of how this works in a little example. We have 2 weights initially, the one at the endpoints of the function, and then we use our linear program to find the point with maximum regret bound. That's the weight W3. And we just add that to our set. So this will be our new sample. We now get 2 new smaller neighborhoods, the blue and the green one, and we compute the respective regret bounds in there. Green is larger here, so that's the next sample that we will be adding. And then we could continue from there and split all the next 3 neighborhoods into smaller neighborhoods, or we just stop here. And we are left with this piecewise linear approximation of this original function, and the error is now illustrated in red. That's actually the regret that we will have. Okay, how does this look like in a robotics problem? We go back to our example from the introduction with the Dubin's curves. And here again, we have the trajectories with the uniform samples and the output of our algorithm. Now we can take a look on the approximation of the optimal cost function. So in the left one, we have the uniform approach again. On the x-axis, we have the weights. So the tangents are just put in uniform increments over that function. However, when the function gets very steep, like at the right-hand end, the tangents lie very far above the actual function, resulting in a large error, resulting in a large regret if you wanted to approximate a solution over there. With our method, we use fewer tangents in places where the function is either almost linear or it's very, very flat. And we put more tangents in the area where all the changes happen. And that leads to a better approximation in that area and therefore to a better, smaller regret overall. Okay, we evaluated this approach in several different planning problems. Here's again a Dubin's planning problem, but now with 3 objectives: length, integral square jerk, and maximum jerk. And we compare the quality for approximating any possible solution using uniform samples and our samples, shown in blue and orange respectively. And let's just focus on the left plot and maybe on the center plot, left showing the maximum absolute regret and the center the relative regret, just the ratio, which is sometimes more interesting.